tonight, I want you to imagine something with me. Picture yourself standing alone in an empty field, far from any city lights. Above you stretches the night sky, and scattered across that darkness are thousands of tiny points of light, each one a sun, burning across unimaginable distances. Some of those suns have worlds circling them, worlds with oceans, mountains, and skies of their own. And on some of those worlds, perhaps right now, someone or something might be looking up at their own night sky, staring at a faint yellow dot, wondering the same thing you are wondering. Are we alone? Here is what makes this question so strange. We have done the math. We have counted the stars. We have discovered the planets. And by every calculation we can make, the answer should be obvious. We should not be alone. The universe should be filled with life, with signals, with evidence of other minds reaching out across the void. But when we listen, we hear nothing. When we look, we see nothing. The cosmos stretches out in every direction, vast beyond comprehension, ancient beyond measure, and utterly, impossibly silent. This is one of the deepest mysteries in all of science. And tonight, we are going to explore it together. Let me give you a sense of just how big the universe actually is, because the numbers alone can change the way you think about this question. The observable universe, the part we can actually see with our telescopes, stretches approximately 93 billion light-years across. That means, if you could somehow travel at the speed of light, the fastest speed possible in our universe, it would take you 93 billion years to cross from one side to the other. For comparison, the entire age of the universe is only 13.8 billion years. The observable universe is so large that light itself has not had time to cross it. Within that unimaginably vast space, astronomers estimate there are somewhere between 200 billion and 2 trillion galaxies. That range is so wide because we simply cannot see them all. Studies using the Hubble Space Telescope suggested the number might be as high as 2 trillion. But more recent observations from probes like New Horizons, which is now outside our solar system, suggest the number might be closer to 200 billion. Either way, the numbers are staggering. Let us use the more conservative estimate. 200 billion galaxies. Each one is a vast collection of stars, gas, dust, and dark matter, spinning slowly through the cosmic darkness. Now, each of those galaxies contains stars. Our own galaxy, the Milky Way, is home to somewhere between 100 billion and 400 billion stars. Some estimates put it closer to 300 billion. The Milky Way is not particularly special in this regard. It is a fairly typical spiral galaxy, shaped like a vast pinwheel with arms of stars sweeping out from a bright central bulge. If you could see it from the outside, it would look like a slow-motion firework frozen in time. Our sun sits about halfway out from the center, in what astronomers sometimes call the galactic suburbs. It is a quiet neighborhood, cosmically speaking, not too close to the chaotic center where stars crowd together and supermassive black holes lurk, not too far out in the sparse outer reaches. Just a modest location in an ordinary galaxy. But here is where things get interesting. Recent discoveries have shown us that planets are everywhere. For most of human history, we knew of only a handful of worlds orbiting our own sun: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. That was it. We had no idea whether other stars had planets at all. But over the past few decades, missions like Kepler and TESS have changed everything. We now know that nearly every star has planets. Many stars have multiple planets dancing around them in intricate cosmic waltzes, and some of those planets sit in what scientists call the habitable zone. This is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Sometimes called the Goldilocks zone. In our own solar system, Earth sits comfortably in this zone. Venus is too close to the sun and too hot. Mars is at the outer edge and is too cold. But Earth is just right. And we now know that billions of other planets in our galaxy alone sit in similar positions around their own stars. Let me put this in perspective. If you take the number of sun-like stars in the Milky Way and multiply it by the fraction that have Earth-sized planets in their habitable zones, you get tens of billions of potentially habitable worlds in our galaxy alone. Not millions, billions. And remember, there are at least 200 billion other galaxies out there. The number of potentially habitable planets in the observable universe is almost beyond comprehension. So here's the question that keeps scientists awake at night. If there are so many places where life could arise, why have we never seen any evidence of it? Where is everybody? This question has a name. It is called the Fermi paradox, named after the brilliant physicist Enrico Fermi, who first asked it over lunch one day in 1950. The paradox is simple to state, but incredibly difficult to answer. Given the size and age of the universe, given the number of stars and planets, given everything we know about chemistry and biology, intelligent life should be common. Civilizations should have arisen millions or even billions of years before us. Some of them should have developed technology. Some of them should have spread across the stars. Some of them should have built things we could see, sent signals we could detect, left evidence we could find. But we have found nothing. No radio signals. No laser pulses. No massive structures blocking starlight. No ancient probes orbiting our sun. No footprints on the moon left by visitors before us. Nothing. The universe appears to be a vast, empty mansion with all the lights off and nobody home. This silence has been called the Great Silence, and it is one of the most troubling puzzles in modern science. Think about the timescales involved. Our universe is 13.8 billion years old. Our sun and Earth formed only about 4.5 billion years ago, making us relative newcomers to the cosmic scene. That means there were billions of years before Earth even existed, when life could have arisen elsewhere. Civilizations could have emerged, flourished, built empires spanning entire galaxies, and then vanished, all before our planet was even a cloud of dust around a young star. Even if we assume that intelligent civilizations are rare, even if only 1 in a million habitable planets ever develops technology, we should still expect millions of civilizations to have existed in our galaxy alone over its 10 billion year history. And if even a tiny fraction of those civilizations developed the desire and ability to spread beyond their home worlds, they could have colonized the entire galaxy many times over. The math is straightforward. A civilization that develops even modest space travel technology, nothing faster than light, nothing fancy, just steady expansion from star to star, could spread across the entire Milky Way in perhaps 10 to 50 million years. That sounds like a long time, but remember, the galaxy is roughly 10 billion years old. There has been more than enough time for hundreds of civilizations to have swept across every corner of our galaxy, settling every habitable world, building structures around every star. And yet, when we look up, we see only stars, silent, distant, alone. This is what makes the Fermi paradox so powerful. It is not just an interesting thought experiment. It is a serious scientific puzzle with real implications for our understanding of life, intelligence, and our place in the cosmos. The absence of evidence for extraterrestrial intelligence is itself a kind of evidence. It tells us something important. We just do not know what. Some scientists think the answer is that we are truly alone. Perhaps life is far more difficult to start than we realize. Perhaps the jump from simple chemistry to living cells is so unlikely that it has only happened once in the entire universe. Perhaps we are the first, the only, a single spark of awareness in an otherwise dead cosmos. Others think the answer is darker. Perhaps civilizations arise all the time, but they do not last. Perhaps there is something about intelligence itself that leads to self-destruction. Perhaps every civilization that develops nuclear weapons eventually uses them. Perhaps every civilization that develops the power to reshape its planet eventually destroys it. Perhaps the universe is not empty because life is rare, but because life is fragile, and civilizations burn out like candles before they can spread to the stars. And still others think the answer might be stranger than we can imagine. Perhaps we are being watched. Perhaps we are in some kind of cosmic zoo, observed by intelligences so far beyond us that we cannot recognize their presence. Perhaps the silence is not absence, but intention. Perhaps the universe is full of life that has chosen, for reasons we cannot understand, to remain hidden. These questions are not just abstract philosophy. They have real consequences for how we think about our own future. If we are alone, then we carry an almost unbearable responsibility. We are the only minds in the universe capable of asking these questions, of appreciating the beauty of the cosmos, of giving meaning to the vast emptiness. If we destroy ourselves, we destroy something irreplaceable. And if we are not alone, if the silence is hiding something, then we must ask ourselves what that means. Are we in danger? Are we protected? Are we simply too primitive to notice the crowded universe around us? Tonight, we are going to explore all of this and more. We are going to trace the history of this question, from Enrico Fermi's casual lunchtime remark to the cutting-edge research being done today. We are going to examine the science behind the paradox, the mathematics of the Drake equation that tries to calculate how many civilizations might exist, the great filter hypothesis that suggests something is preventing civilizations from spreading across the stars. We are going to look at the many possible solutions that scientists have proposed. Maybe interstellar travel is simply too hard. Maybe civilizations choose not to expand. Maybe they are hiding. Maybe they have evolved beyond physical form into something we cannot detect. Maybe they are already here, and we simply have not noticed. And we are going to think about what all of this means for us, for our future, for our place in the grand story of the cosmos. But before we go any further, I want you to hold on to that image we started with. You standing in an empty field, looking up at the stars, each one a sun, many of them circled by worlds. Some of those worlds with conditions that could support life. And yet, despite all the billions of opportunities, all the trillions of years, all the countless chances for someone else to be out there, the sky remains silent. That silence is the mystery at the heart of our journey tonight. It is a silence that has puzzled the greatest minds of our time. A silence that forces us to confront the deepest questions about existence, intelligence, and what it means to be alive in this vast and ancient universe. The stars are waiting. The questions are waiting. And somewhere out there, perhaps, so is the answer. Let us begin. To truly understand the Fermi paradox, we need to grasp something that the human mind was never designed to comprehend. We need to understand just how big the universe actually is. And I want to warn you right now, These numbers are going to sound impossible. They are going to stretch your imagination beyond anything you have ever contemplated. But every single one of them is real, verified by decades of observation with the most powerful instruments humanity has ever built. Let us start with what we can see. The observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang, stretches approximately 93 billion light-years across. Now, a light-year is the distance that light travels in 1 year, and light moves at about 300,000 kilometers per second. That is fast enough to circle the Earth 7.5 times in a single second. Yet even at that incredible speed, light takes 93 billion years to cross the observable universe from one end to the other. But here is where it gets strange. The universe is only 13.8 billion years old. How can light have traveled 93 billion light years in only 13.8 billion years? The answer is that space itself has been expanding ever since the Big Bang. The light that started its journey toward us billions of years ago has been traveling through space that keeps stretching, like dots on a balloon that is being inflated. By the time that ancient light reaches our telescopes, the objects that emitted it have moved much farther away than the distance the light has traveled. And here is something even more humbling. The observable universe is almost certainly just a tiny fraction of the entire universe. We have no way of knowing how big the whole thing is. It could extend for trillions of light years beyond what we can see. It could be infinite. We simply do not know, and we may never know, because information cannot travel faster than light, and there are regions of space from which light will never reach us, no matter how long we wait. Within this observable portion, astronomers have counted the galaxies. Early estimates using the Hubble Space Telescope suggested there might be around 200 billion galaxies. But in 2016, a team led by Christopher Consolis at the University of Nottingham analyzed deep space images and concluded that the true number might be at least 10 times higher, perhaps as many as 2 trillion galaxies. Many of these are too faint and too distant for our current telescopes to see directly, but mathematical models suggest they must exist based on the distribution of galaxies we can observe. More recent studies using data from probes like New Horizons, which is now beyond Pluto and can measure background light without interference from our solar system, suggest the number might be somewhat lower, perhaps between 200 billion and 2 trillion. Either way, we are talking about hundreds of billions of galaxies at minimum. Each of those galaxies is a vast island of stars. Some are small dwarf galaxies with just a few billion stars. Others are giant elliptical galaxies containing trillions. Our own Milky Way falls somewhere in the middle, a barred spiral galaxy that astronomers estimate contains between 100 billion and 400 billion stars. The most commonly cited figure is around 200 to 300 billion stars. If you tried to count them one per second, it would take you roughly 10,000 years just to count the stars in our galaxy alone. The Milky Way has a distinctive shape. If you could see it from outside, it would look like a vast cosmic pinwheel, a flat disk of stars with graceful spiral arms sweeping out from a bright central bulge. The disk spans about 100,000 to 180,000 light-years across, though some recent estimates suggest it might be even larger, perhaps 200,000 light-years when you include the faint outer regions. The disk is relatively thin, only about 1,000 light-years thick at the spiral arms, though it bulges to about 10,000 light-years at the center. Our Sun sits in this disk, about 27,000 light-years from the galactic center. We are located in what astronomers sometimes call the galactic suburbs, on the inner edge of a minor spiral arm called the Orion Arm, sometimes called the Orion Spur. It is a quiet neighborhood, cosmically speaking. We are far enough from the chaotic galactic center, where stars crowd together, and a supermassive black hole called Sagittarius A star lurks, weighing in at about 4 million times the mass of our sun. But we are not so far out that we are in the sparse outer reaches where heavy elements are rare. This position matters. Scientists have identified something called the galactic habitable zone, a ring-shaped region around the galactic center where conditions might be most favorable for life. Too close to the center, and you face intense radiation, frequent supernovae, and gravitational chaos from passing stars. Too far out, and there may not be enough heavy elements like carbon, oxygen, and iron to build rocky planets and complex chemistry. The galactic habitable zone is thought to lie between about 7 and 9 kiloparsecs from the center, roughly 23,000 to 29,000 light-years. Our sun sits right in this sweet spot. But the Milky Way is not just vast in space, it is ancient in time. The galaxy formed roughly 13 billion years ago, not long after the Big Bang itself. Our sun and solar system, by contrast, formed only about 4.5 billion years ago. That means the Milky Way had been producing stars for more than 8 billion years before our sun even existed. Countless stellar generations lived and died, forging heavy elements in their cores and scattering them across the galaxy when they exploded as supernovae. We are literally made of the ashes of dead stars. Now here is where the numbers become truly staggering. For most of human history, we knew of only 8 planets, the worlds circling our own sun. We had no idea whether planets existed around other stars. They were too small and too faint to see across interstellar distances. But that changed in 1995, when astronomers Michel Mayor and Didier Queloz detected a planet orbiting the star 51 Pegasi about 50 light-years away. It was a gas giant larger than Jupiter, orbiting impossibly close to its star. Nothing like it existed in our solar system. That discovery opened the floodgates. The Kepler Space Telescope, launched by NASA in 2009, revolutionized our understanding of planetary systems. Over 9 years of operation, Kepler stared at a patch of sky containing about 150,000 stars, watching for the tiny dips in brightness that occur when a planet passes in front of its star. By the time it retired, Kepler had discovered more than 2,600 confirmed exoplanets and identified thousands more candidates. Its successor, the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018 and has continued the search, focusing on nearby, bright stars. What these missions revealed transformed our understanding of the cosmos. Planets are not rare anomalies. They are everywhere. Astronomers now estimate that virtually every star in the galaxy has at least one planet, and many have multiple planets. The Milky Way alone likely contains at least 100 billion planets, and possibly several times that number. But not all planets are equal when it comes to the possibility of life. What matters is whether a planet sits in what scientists call the habitable zone, the range of distances from a star where temperatures could allow liquid water to exist on a planet's surface. Too close, and water boils away. Too far, and it freezes solid. The habitable zone is sometimes called the Goldilocks zone because conditions there are not too hot, not too cold, but just right. The size of the habitable zone depends on the star. For hot, bright stars, it lies farther out. For cool, dim stars, it is much closer in. Our sun is a G-type yellow dwarf, a medium-sized star with a habitable zone that currently extends from about 0.95 to 1.37 astronomical units from the sun, where 1 astronomical unit is the distance from Earth to the Sun. Earth sits comfortably within this zone, while Venus, at 0.72 astronomical units, is too close and has become a scorching hellscape. Mars, at 152 astronomical units, is at the outer edge and has lost most of its atmosphere and surface water. Using data from Kepler and other surveys, scientists have estimated that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. That works out to about 11 billion potentially habitable planets orbiting Sun-like stars in our galaxy alone. But Sun-like stars are not the most common type. Red dwarf stars, smaller and cooler than our Sun, make up about 70% of all stars in the Milky Way. If we include planets in the habitable zones of red dwarfs, the number could be as high as 40 billion Earth-sized worlds in habitable zones throughout our galaxy. 40 billion. Let that number sink in. 40 billion worlds where conditions might be right for liquid water, for chemistry, for life. And that is just in our galaxy. Multiply that by the hundreds of billions of other galaxies in the observable universe, and you are looking at a number so large it defies human comprehension. Billions upon billions upon billions of potential homes for life. And here is the factor that makes the Fermi paradox so sharp. Time. The Milky Way is roughly 13 billion years old. Our Sun is only 4.5 billion years old. That means other stars, other planets, other potential civilizations had billions of years of head start on us. The oldest stars in our galaxy are nearly as old as the universe itself. If life arose on a planet orbiting one of those ancient stars even a billion years before it arose on Earth, that civilization would have had a billion years more than us to develop technology, to spread across the stars, to make their presence known. A billion years is an almost inconceivable span of time. A billion years ago on Earth, the most complex life forms were single-celled organisms. In a billion years, we went from bacteria to human civilization. What could another civilization accomplish in a billion years? They could have colonized every star in the galaxy. They could have built structures visible across interstellar distances. They could have filled the cosmos with signals, with probes, with evidence of their existence. And yet, when we look out at the universe, we see nothing. No signals, no structures, no visitors, just stars burning silently in the dark. This is the heart of the paradox. The numbers say the universe should be teeming with life. The silence says it is not. One of these conclusions must be wrong. Either our assumptions about the prevalence of life are mistaken, or there is something about the universe, about civilizations, about existence itself, that we do not yet understand. The answer, whatever it turns out to be, will tell us something profound about our place in the cosmos and about what the future might hold for our own civilization. But to understand how we arrived at this puzzle, we need to go back to a summer afternoon in 1950, to a lunch conversation among physicists that would change how we think about life in the universe forever. The summer of 1950 was a strange time in America. The country stood at the dawn of the atomic age, both terrified and exhilarated by the power that science had unleashed upon the world. Just 5 years earlier, the first atomic bombs had fallen on Hiroshima and Nagasaki, ending the Second World War and beginning something new, something nobody quite understood. The Cold War was taking shape. The Soviet Union had detonated its own atomic bomb the previous year. Senator Joseph McCarthy was beginning his crusade against supposed communist infiltrators. And across the nation, people were reporting strange lights in the sky. It was against this backdrop that one of the most significant scientific questions of the 20th century was casually posed over lunch. Enrico Fermi was, by 1950, one of the most famous physicists in the world. Born in Rome in 1901, he had displayed extraordinary mathematical ability from childhood. By his mid-20s, he was already making fundamental contributions to quantum mechanics and nuclear physics. In 1938, he won the Nobel Prize for his work on induced radioactivity and his discovery of new elements produced by neutron bombardment. That same year, he used the Nobel ceremony in Stockholm as an opportunity to escape Mussolini's Italy with his Jewish wife, Laura, and emigrate to the United States. In America, Fermi's brilliance found new purpose. He joined Columbia University and then the University of Chicago, where in December 1942, he achieved one of the most significant technological breakthroughs in human history. In a converted squash court beneath the university's football stadium, Fermi and his team created the world's first controlled, self-sustaining nuclear chain reaction. It was the proof of concept that made the atomic bomb possible. From there, Fermi joined the Manhattan Project at Los Alamos National Laboratory in New Mexico, where he worked alongside Robert Oppenheimer, Edward Teller, and dozens of other brilliant scientists to develop the weapons that would reshape global politics forever. By 1950, Fermi was a regular visitor to Los Alamos, consulting on various projects related to nuclear weapons development. He was known among his colleagues not only for his extraordinary scientific intuition, but also for a particular type of question that came to bear his name: Fermi questions or Fermi problems. These were seemingly impossible estimation puzzles that could nonetheless be solved through careful reasoning and educated guesses. How many piano tuners are there in Chicago? How many atoms of Caesar's last breath do you inhale with each breath you take? Fermi delighted in showing that with the right approach, you could estimate almost anything. It was in this spirit that Fermi posed his most famous question. The exact date has been lost to history, but we know it was summer 1950. We know this because of a cartoon. Eric Jones, a Los Alamos scientist, managed to reconstruct the conversation decades later through letters to the surviving participants. The witnesses, Emil Konopinski, Edward Teller, and Herbert York, all remembered that on the walk to lunch at Fuller Lodge, the conversation had turned to a recent cartoon in the New Yorker magazine. The drawing, by Alan Dunn, showed little green men emerging from a flying saucer in New York City and stealing trash cans. It was a humorous reference to two unexplained phenomena of the time: the rash of UFO sightings sweeping the nation and a mysterious epidemic of trash can thefts in New York. The cartoon led naturally to a discussion of flying saucers and whether extraterrestrial visitors might be real. The physicists joked about the feasibility of faster-than-light travel and whether the reported saucers could possibly be alien spacecraft. It was lighthearted banter among colleagues, the kind of speculative conversation that scientists often enjoy. But as the group sat down to lunch, the conversation moved on to other topics. Then, according to Edward Teller's account, something unexpected happened. In the middle of an unrelated discussion, Fermi suddenly blurted out a question that seemed to come from nowhere. The wording has been recalled differently by different witnesses. Teller remembered it as, "Where is everybody?" Konopinski recalled it as, "But where is everybody?" York remembered a longer discussion. What struck everyone at the table was that, despite the question coming completely out of context, everybody immediately understood what Fermi was asking. He was asking about extraterrestrials. The earlier conversation about flying saucers had set his mind working, and now he had arrived at something profound. Teller later wrote that the question provoked general laughter, not because it was silly, but because of the strange fact that, in spite of Fermi's question coming out of the blue, everybody around the table seemed to understand at once that he was talking about extraterrestrial life. There was something in the way Fermi asked the question, something in its simple directness that cut through to the heart of a deep puzzle. According to Herbert York's recollection, Fermi did not simply ask the question and leave it hanging. He followed up with what York called a series of calculations on the probability of Earth-like planets, the probability of life given an Earth, the probability of humans given life, the likely rise and duration of high technology, and so on. This was Fermi doing what Fermi did best, breaking down an impossibly complex question into a series of estimable factors, each of which could be reasoned about, and multiplying them together to arrive at an answer. Fermi's conclusion, as York remembered it, was striking. Based on his back-of-the-envelope calculations, we ought to have been visited long ago and many times over. This was the paradox in its original form. The galaxy is old. The number of stars is immense, even with conservative assumptions about how often planets form, how often life arises, and how often intelligence evolves. The numbers suggested that civilizations should have had more than enough time to spread throughout the galaxy. They should be here. They should be obvious. And yet, there was no evidence of their presence. Edward Teller's recollection was somewhat different. He remembered that Fermi did not elaborate much beyond the initial question, and that the conversation ended with perhaps a statement that the distances to the next location of living beings may be very great, and that indeed, as far as our galaxy is concerned, we are living somewhere in the sticks, far removed from the metropolitan area of the galactic center. In other words, perhaps we are simply too remote, too isolated, too insignificant to have attracted any attention. Fermi himself never published anything on the topic. He died of stomach cancer in 1954, just 4 years after that fateful lunch conversation. The question he posed might have been forgotten, a curious footnote in the history of physics, if not for what came later. But before we get to that, it is worth noting that Fermi was not the first to contemplate the apparent absence of extraterrestrials. The question has roots stretching back centuries. In 1686, the French writer Bernard Le Bovier de Fontenelle published Conversations on the Plurality of Worlds, a popular work that speculated about life on other planets. In 1865, Jules Verne's novel From the Earth to the Moon imagined a voyage to our nearest celestial neighbor. And in 1933, the Soviet rocket scientist Konstantin Tsiolkovsky, one of the founding figures of astronautics, wrote about the apparent contradiction between the likelihood of extraterrestrial civilizations and the absence of any evidence for them. Tsiolkovsky proposed his own solution. Perhaps advanced civilizations deliberately quarantine younger species like humanity, allowing them to develop independently. This idea would later be reinvented as the zoo hypothesis. But it was Fermi's formulation, with its characteristic directness and its grounding in basic physics and mathematics, that would come to define the problem. The question first appeared in print in 1963, in a footnote to a paper by Carl Sagan. 2 years later, Stephen Dole noted the dilemma at a scientific symposium, asking, if there are so many advanced forms of life around, where is everybody? Though he did not attribute the question to Fermi. The phrase, "Where are they?" appeared as a chapter heading in the 1966 book Intelligent Life in the Universe, co-authored by Sagan and the Soviet astronomer Yosef Shklovsky. The paradox remained something of a curiosity until 1975, when astrophysicist Michael Hart published a landmark paper in the Quarterly Journal of the Royal Astronomical Society, titled An Explanation for the Absence of Extraterrestrials on Earth. Hart laid out the argument with mathematical rigor, Given the age of the galaxy and the time required for a civilization to spread from star to star, even using relatively slow spacecraft, the entire Milky Way could have been colonized many times over. The fact that no extraterrestrials were present on Earth or had left any obvious evidence of their existence led Hart to a stark conclusion. We are the first civilization in our galaxy. Hart proposed 4 broad categories of possible explanations. First, there might be some physical barrier that makes interstellar travel impossible or impractical. Second, there might be sociological factors. Civilizations might choose not to explore or expand for reasons of their own. Third, there might be temporal factors. Perhaps civilizations have not had enough time to reach us. And fourth, perhaps extraterrestrials have already visited Earth, but we do not recognize the evidence. Hart rejected the first 3 possibilities as inadequate and was skeptical of the fourth, concluding that the most likely explanation was simply that extraterrestrial civilizations did not exist. The paper sparked intense debate. The following year, the physicist Frank Tipler published a response arguing even more forcefully that extraterrestrial intelligent beings do not exist. Tipler pointed out that any civilization could send self-replicating probes throughout the galaxy, machines that would travel to a star system, use local resources to build copies of themselves, and then send those copies onward to other stars. Such a strategy could explore the entire galaxy in just a few million years, a blink of an eye on cosmic timescales. The fact that no such probes had been detected, Tipler argued, was strong evidence that nobody had ever launched them. The term Fermi paradox itself was coined in 1977 by David Stevenson in an article in the Journal of the British Interplanetary Society. The name stuck, and the paradox became one of the central questions in the emerging field of astrobiology. The impact was significant and not always positive. The paradox damaged efforts to fund the search for extraterrestrial intelligence. In the United States, Senator William Proxmire cited Tipler's arguments when he successfully pushed to terminate federally funded SETI research in the early 1980s. Why search for something that probably does not exist? But others saw the paradox differently. Far from proving that we are alone, the apparent absence of extraterrestrials might be telling us something important about the nature of life, intelligence, and civilization. Perhaps the conditions for complex life are rarer than we thought. Perhaps civilizations tend to destroy themselves before they can spread to the stars. Perhaps they are out there, but have chosen to remain hidden. Perhaps the galaxy is indeed full of life, and we simply have not looked hard enough or long enough to find it. These questions remain open today, more than 7 decades after Fermi's casual lunchtime remark. And to begin answering them, we need a way to organize our thinking, a framework for estimating how many civilizations might exist and where the bottlenecks might lie. That framework would come just over a decade after Fermi's question, from a young radio astronomer who had just conducted humanity's first scientific search for signals from the stars. In the spring of 1960, a 29-year-old astronomer named Frank Drake pointed an 85-foot radio telescope at the stars and listened for voices from another world. It was humanity's first systematic scientific attempt to detect intelligent life beyond Earth, and it would set in motion a chain of events that continues to this day. Frank Drake was born in Chicago in 1930 and showed an early fascination with the stars. He studied astronomy at Cornell University and completed his graduate work at Harvard. In 1958, he took a position at the National Radio Astronomy Observatory in Green Bank, West Virginia. a remote facility nestled in the mountains where radio telescopes could operate free from the electronic interference of cities. Drake was drawn to a radical idea. If intelligent civilizations existed elsewhere in the galaxy, and if they had developed radio technology as Earth had done, then they might be broadcasting signals into space. Those signals, traveling at the speed of light, could potentially be detected by sensitive radio telescopes. All you had to do was point your antenna at the right star and tune to the right frequency. The concept had been outlined the previous year in a paper by physicists Giuseppe Cocconi and Philip Morrison, published in the journal Nature. They argued that the most logical frequency for interstellar communication would be around 1420 megahertz, the frequency at which hydrogen atoms naturally emit radio waves. Hydrogen is the most abundant element in the universe, and any civilization with basic knowledge of physics would know this frequency. It was a natural cosmic meeting point, a place where listeners and broadcasters might converge. Drake was captivated by the idea. With the support of the observatory's director, Otto Struve, he designed an experiment to search for artificial signals from two nearby sun-like stars, Tau Ceti, about 12 light-years away in the constellation Cetus, and Epsilon Eridani, about 10.5 light-years away in the constellation Eridanus. Both stars were relatively similar to our Sun, and therefore might have planets capable of supporting life. Drake named his experiment Project Ozma, after the princess who ruled the faraway, exotic land of Oz in L. Frank Baum's children's books. It was a fitting name for a search targeting distant, potentially inhabited worlds. For about 150 hours spread over 4 months, from April to July 1960, Drake's team listened. The equipment was simple by today's standards: a single radio receiver tuned to frequencies near the hydrogen line, a chart recorder to capture any signals, and a loudspeaker so the team could hear what the telescope was picking up. Mostly, they heard static, the random crackle of cosmic background noise. There was one heart-stopping moment. Early in the project, while pointed at Epsilon Eridani, the equipment detected a strong, pulsing signal. For a few tense minutes, the team wondered if they had made contact, but the signal disappeared when they moved the telescope and reappeared when they pointed it elsewhere, suggesting it was coming from Earth, not the stars. Later investigation revealed it was probably interference from a high-altitude aircraft on a secret military mission. Project Ozma detected no extraterrestrial signals. The stars remained silent, but the experiment captured the public imagination in ways Drake had not anticipated. Here was a serious scientific effort to answer one of humanity's oldest questions. Are we alone? The media coverage was enormous, and scientists around the world took notice. The attention led to an invitation that would shape the future of the search for extraterrestrial intelligence. J. Peter Pearman, a staff officer at the National Academy of Sciences, approached Drake about organizing a small conference to discuss whether searching for alien signals was a worthwhile scientific endeavor. Should resources be devoted to this effort? What were the chances of success? How should such a search be conducted? Drake agreed to host the meeting at Green Bank in November 1961. He invited about a dozen scientists from various fields. Anyone he could think of who might have relevant insights. The final guest list read like a who's who of 20th century science. It included Philip Morrison, co-author of the original paper advocating radio searches for extraterrestrial intelligence. It included Carl Sagan, then a brilliant young astronomer just 27 years old, who would later become the most famous science communicator of his generation. It included Melvin Calvin, a biochemist who would receive a phone call during the conference informing him that he had just won the Nobel Prize in Chemistry. It included John Lilly, a neuroscientist studying dolphin communication. It included Barney Oliver, a pioneer in electronics, and Dana Atchley, a radio enthusiast and businessman. And it included Otto Struve, the observatory director who had supported Drake's original experiment. As Drake prepared for the conference, he realized he needed an agenda, some structure to guide the discussions. The problem was that nobody had ever held a scientific meeting on this topic before. There was no established framework, no agreed-upon set of questions. A few days before the conference, Drake sat down and tried to identify all the factors that would determine whether a search for extraterrestrial signals could succeed. What did you need to know to estimate how many civilizations might be out there, transmitting signals that we could detect? He wrote down a series of questions, starting with the broadest astronomical factors and narrowing down to the most speculative biological and sociological ones. Then he realized that if you multiplied all these factors together, you would get a number, the number of communicating civilizations in the galaxy right now. The result was a simple equation that would become one of the most famous formulas in science. It is known as the Drake equation, and it can be written as N equals R star times Fp times Ne times Fl times Fi times Fc times L. Let me explain what each term means. N is the number we are trying to estimate, the number of civilizations in our galaxy whose electromagnetic emissions, like radio or laser signals, are detectable right now. R star is the rate at which new stars form in the galaxy, measured in stars per year. This is the one factor that was reasonably well known even in 1961. Astronomers estimated that, averaged over the life of the galaxy, about 1 to 3 new stars form per year. Fp is the fraction of those stars that have planetary systems. In 1961, this was completely unknown. There was no proof that any star besides our Sun had planets. Today, thanks to missions like Kepler and TESS, we know that planets are extremely common. Nearly every star has at least one planet, so Fp is close to 1. Ne is the average number of planets per star that could potentially support life. This usually means rocky planets in the habitable zone, the region where liquid water could exist. Current estimates suggest there might be between 0.5 and 2 such planets per Sun-like star. Fl is the fraction of potentially habitable planets where life actually arises. This is where things get speculative. Life arose on Earth very quickly in geological terms, within a few 100 million years of the planet cooling enough to be habitable. This suggests life might arise fairly easily when conditions are right. But we have a sample size of exactly 1, so we cannot be certain. Fi is the fraction of life-bearing planets where intelligent life evolves. Life has existed on Earth for about 3.8 billion years, but intelligent, tool-using life has existed for only a few million years at most. Intelligence might be a common outcome of evolution, or it might be an extremely rare fluke. Fc is the fraction of intelligent species that develop civilizations capable of and interested in interstellar communication. Here we must ask whether intelligence inevitably leads to technology, whether technology inevitably leads to radio or other detectable emissions, and whether civilizations choose to broadcast their presence. Finally, L is the length of time that such civilizations continue to emit detectable signals, measured in years. This is perhaps the most uncertain and most troubling factor of all. A civilization might broadcast for millions of years, becoming a permanent fixture in the cosmic community, or it might destroy itself within a few centuries of developing advanced technology, vanishing before anyone else can detect it. Drake never intended his equation to give a precise answer. He created it as a framework for discussion, a way to organize thinking about an immensely complex problem. As the famous astronomer Jill Tarter later put it, the Drake equation is a wonderful way to organize our ignorance. At the 1961 Green Bank Conference, the attendees went through each factor, debating the likely values and their uncertainties. They did not reach a consensus, but Drake's own estimate at the time was optimistic. He suggested that N, the number of communicating civilizations in the galaxy, might be around 10,000. The galaxy might be scattered with technological species, each one broadcasting into the void, waiting for a response. The conference participants were so enthusiastic about their discussions that they gave themselves a playful name, the Order of the Dolphin, in honor of John Lilly's work on dolphin communication. They commemorated their gathering with a plaque that still hangs at the Green Bank Observatory. In the decades since, the Drake equation has been both celebrated and criticized. Its strength is its clarity. It breaks down an overwhelming question into a series of smaller questions that can, in principle, be investigated individually. As we learn more about each factor, we can refine our estimate of N, and we have learned a great deal. The Kepler mission, in particular, transformed our understanding of the first few factors. We now know that planets are not rare but ubiquitous. We know that rocky planets in habitable zones are common. The early terms of the equation have moved from pure speculation to reasonably well-constrained estimates, but the later factors remain stubbornly uncertain. We do not know how often life arises on habitable planets because we have never detected life anywhere except Earth. We do not know how often intelligence evolves because we have only one example. And we do not know how long technological civilizations last because, again, we have only ourselves, and we have been a technological civilization for barely a century. Some researchers have tried to address these uncertainties through statistical analysis. In 2016, Adam Frank and Woodruff Sullivan at the University of Rochester proposed what they called the archaeological form of the Drake equation. Instead of asking how many civilizations exist right now, they asked how many civilizations have ever existed in the history of the observable universe. This reformulation avoids the thorny question of how long civilizations last. Their calculation was sobering. For humanity to be the only technological civilization that has ever existed anywhere in the observable universe, the probability of a civilization arising on a habitable planet would have to be less than about 1 in 10 billion trillion. That is an extraordinarily small number. It suggests that unless the development of intelligent, technological life is almost impossibly rare, other civilizations have almost certainly existed somewhere in the cosmos at some point in the past 13.8 billion years. But that does not mean they exist now, and it does not mean they existed anywhere close enough in space or time for us to have any chance of detecting them. This is the frustration of the Drake equation. It tells us that the universe could be full of civilizations, or it could be almost empty. The difference comes down to the values of factors we cannot yet measure. Until we develop better ways to search for life and better ways to understand the longevity of technological societies, the equation remains more of a guide to our ignorance than a tool for answering questions. And yet, for all its limitations, the Drake equation has served an essential purpose. It gave scientists a common language for discussing the search for extraterrestrial intelligence. It identified the key questions that need to be answered, and it inspired generations of researchers to build better telescopes, develop new search strategies, and keep listening for that signal from the stars that might one day tell us we are not alone. Frank Drake continued his work in SETI for the rest of his career. In 1974, he helped compose the Arecibo message, humanity's first deliberate radio transmission to extraterrestrial civilizations, beamed from the Arecibo radio telescope in Puerto Rico toward a globular cluster 25,000 light-years away. He served as president of the SETI Institute and mentored countless younger scientists. He died in September 2022 at the age of 92, having devoted his life to one of the most profound questions humans have ever asked. The equation he created remains as relevant today as it was in 1961, and as we continue to fill in its terms, one by one, we may eventually learn whether the universe is teeming with life or whether we truly are alone in the cosmic dark. Of all the possible answers to the Fermi paradox, the most unsettling might be the simplest. What if the universe really is empty? What if we are truly, cosmically, utterly alone? What if Earth is not just rare, but unique? The only place in all the hundreds of billions of galaxies where complex life has ever arisen. This is the essence of what has come to be called the rare Earth hypothesis, and it stands in stark contrast to the optimistic assumptions that underlie much of the search for extraterrestrial intelligence. The hypothesis was given its name and its most thorough scientific treatment in a book published in the year 2000. The authors were Peter Ward, a paleontologist and geologist at the University of Washington, and Donald Brownlee, an astronomer and astrobiologist at the same institution. Their book, titled Rare Earth: Why Complex Life is Uncommon in the Universe, challenged the prevailing wisdom of the day. For decades, scientists like Carl Sagan and Frank Drake had argued for what is sometimes called the principle of mediocrity, or the Copernican principle. This principle holds that Earth is not special. We orbit an ordinary star in an ordinary galaxy in an ordinary part of the universe. If the conditions that allowed life to arise here are not special, then similar conditions should exist elsewhere. Life, therefore, should be common. Ward and Brownlee turned this argument on its head. Yes, they agreed. The basic ingredients for life might be widespread. Simple microbial life, bacteria and archaea, might be relatively common in the universe. But complex life, the kind that builds cities and radio telescopes and wonders about its place in the cosmos, that is another matter entirely. Complex life, they argued, requires such a specific and improbable combination of conditions that it might be extraordinarily rare. Earth might not be typical at all. Earth might be a freak. Their argument rests on a long list of factors that appear to have been essential for the evolution of complex life on Earth. Each factor, taken individually, might not seem impossibly rare. But when you multiply them all together, when you consider that all of them had to be present simultaneously for billions of years, the odds start looking very slim. Let us go through some of these factors, starting with our position in the galaxy. We have already discussed the galactic habitable zone, the ring-shaped region where conditions might be most favorable for life. Ward and Brownlee argued that this zone is narrower than many scientists had assumed. Too close to the galactic center, and you face intense radiation from the crowded stars, frequent nearby supernovae that could sterilize entire solar systems, and gravitational perturbations from passing stars that could destabilize planetary orbits. Too far from the center, and there are not enough heavy elements to build rocky planets and complex chemistry. Life needs carbon, oxygen, nitrogen, iron, and dozens of other elements that are only produced in the cores of massive stars and scattered by supernova. In the outer reaches of the galaxy, these elements are scarce. Our sun sits in a fortunate position, roughly halfway between the galactic center and the edge. But even this is not enough. The Sun also happens to have a nearly circular orbit around the galactic center, and its orbital period is almost perfectly synchronized with the rotation of the galaxy's spiral arms. This means we rarely pass through a spiral arm, where star formation is intense and supernovae are common. Most stars are not so lucky. They plunge through spiral arms periodically, exposing any planets they might have to bursts of deadly radiation. Then there is the Sun itself. Our star is a G-type yellow dwarf, a medium-sized, medium-temperature star that will burn steadily for about 10 billion years. This is crucial. Life on Earth took about 4 billion years to evolve from simple microbes to complex animals. A star that burned out too quickly would not give evolution enough time. A star that flared violently would sterilize its planets. A star that was too dim would require planets to orbit so close that they became tidally locked, with one side perpetually facing the star and one side in eternal darkness. Most stars in the galaxy are not like our Sun. About 70% are red dwarfs, smaller and cooler and far more volatile. Red dwarfs frequently erupt with powerful flares that could strip away a planet's atmosphere and irradiate its surface. Their habitable zones are so close to the star that any planets there would almost certainly be tidally locked. Whether complex life could evolve on such a world is an open question, but the challenges would be immense. Now consider our solar system's architecture. Jupiter, the giant planet that dominates the outer solar system, has played a crucial role in Earth's history. Jupiter's immense gravity acts as a cosmic shield, deflecting or capturing many of the comets and asteroids that might otherwise rain down on the inner planets. Without Jupiter, Earth might have suffered far more devastating impacts over its history, and life might never have had the chance to evolve beyond simple forms. But Jupiter cannot be too close either. A giant planet in the wrong orbit could gravitationally eject Earth-like planets from the habitable zone or send them spiraling into the Sun. Then there is the Moon. Earth's moon is unusually large compared to its planet, much larger in proportion than any other moon in the inner solar system. The Moon is thought to have formed about 4.5 billion years ago when a Mars-sized object collided with the early Earth, throwing debris into orbit that eventually coalesced into our satellite. This impact also tilted Earth's axis to about 23.5 degrees, which gives us our seasons. The Moon has done more than provide romantic lighting for poets. Its gravitational pull stabilizes Earth's axial tilt, preventing the wild wobbles that would otherwise cause catastrophic climate swings. Mars, which has no large moon, has experienced axial tilts ranging from about 10 degrees to over 60 degrees throughout its history, causing extreme climate variations that may have prevented any life from gaining a foothold. The Moon also powers the tides, which may have been important in the early chemistry that led to life, and its formation may have helped remove certain elements from Earth's early atmosphere that would have been hostile to life. Earth itself has properties that may be essential for complex life. Our planet has a molten iron core that generates a powerful magnetic field, the magnetosphere. This invisible shield deflects the solar wind and cosmic radiation that would otherwise strip away our atmosphere and irradiate the surface. Mars once had a magnetic field, but it died billions of years ago when its core cooled. And without that protection, the solar wind gradually stripped away most of its atmosphere. Today, Mars is a cold, dry, radiation-bathed desert. Earth also has plate tectonics, a process in which the planet's outer shell is divided into huge plates that slowly move, colliding, separating, and sliding past each other over millions of years. Plate tectonics might seem unrelated to life, but Ward and Brownlee argued that it is essential. Plate tectonics drives the carbon cycle, pulling carbon dioxide out of the atmosphere through weathering and subducting it into the mantle, then releasing it again through volcanic eruptions. This thermostat has kept Earth's climate stable enough for liquid water to exist continuously for billions of years. Without plate tectonics, Earth might have suffered a runaway greenhouse effect like Venus or a frozen fate like Mars. Plate tectonics also creates diverse environments, mountains and ocean basins and volcanic islands that encourage evolutionary diversification. It recycles nutrients and creates the varied habitats where different species can evolve and thrive. Even water, so common that we take it for granted, might be rarer than we think. Earth has just the right amount of water, enough to fill the oceans without drowning the continents entirely. Too much water, and you have a water world with no land, no weathering, no diverse environments. Too little, and you have a desert planet. Where Earth's water came from is still debated. It may have been delivered by comets and asteroids during the early bombardment of the solar system, or it may have been incorporated into the planet as it formed. Either way, the amount was just right. Even Earth's atmosphere seems fortuitously composed. The presence of oxygen, which makes up about 21% of our atmosphere today, is essential for complex animal life. But oxygen was not always present. For the first 2 billion years of Earth's history, the atmosphere had almost no free oxygen. Then, around 2.4 billion years ago, photosynthetic cyanobacteria began producing oxygen as a waste product. This event, called the Great Oxygenation Event, gradually transformed the atmosphere and made animal life possible. But it also triggered one of the most severe ice ages in Earth's history, the Snowball Earth events, which nearly wiped out life entirely. The rise of oxygen was a bottleneck that life barely squeezed through. And then there is the question of evolution itself. Even if all the physical conditions are right, there is no guarantee that evolution will produce intelligent, technological life. For more than 3 billion years, life on Earth consisted only of single-celled organisms. The jump to multicellular life happened only once, and it may have been an extremely improbable event. The jump to complex animals happened only around 540 million years ago, in the Cambrian explosion. The evolution of intelligence and technology happened only in one lineage, our own, and only in the last few million years. The paleontologist Charles Lineweaver has argued that intelligence is not a convergent feature of evolution. Unlike eyes, which have evolved independently dozens of times, or flight, which evolved independently in insects, birds, bats, and pterosaurs, intelligence of the human type seems to have evolved only once. This suggests that it may require a very specific and unlikely sequence of events, not a general trend that natural selection favors. Ward and Brownlee acknowledged that simple microbial life might be common in the universe. Bacteria are tough. They can survive in boiling hot springs and frozen Antarctic lakes, in acidic pools in the crushing depths of the ocean floor. If there is liquid water anywhere in the cosmos, simple life might find a way to exist there. But complex life, animals and plants and intelligent beings, that requires so much more. It requires the right star in the right part of the right kind of galaxy. It requires a rocky planet with the right composition, the right amount of water, the right atmosphere, the right magnetic field, the right plate tectonics. It requires a large moon and a protective gas giant. It requires billions of years of stability, and it requires a series of evolutionary transitions that may each have been vanishingly unlikely. Multiply all these probabilities together, and you might conclude that Earth is not just rare, but unique. In a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, Earth might be the only place where someone is wondering whether they are alone. This is a sobering thought. It is also, in a sense, a comforting one. If we are alone, then we are precious beyond measure. We are the only minds in the universe capable of appreciating its beauty, of understanding its laws, of asking questions about its meaning. The responsibility that places on us is almost too great to contemplate. But not everyone accepts the rare Earth hypothesis. Critics have pointed out that Ward and Brownlee may have been too restrictive in their criteria, assuming that life elsewhere must evolve exactly as it did on Earth. Perhaps alien life could evolve under very different conditions, using different chemistry, adapting to environments that we would consider hostile. The discovery of extremophiles on Earth, organisms thriving in places we once thought impossible for life, suggests that nature is more resourceful than we imagined. Still, the rare Earth hypothesis remains a serious contender among solutions to the Fermi paradox. It reminds us that the universe might not be the crowded, chattering place that science fiction has led us to expect. The silence we hear from the stars might not be a puzzle at all. It might simply be the sound of emptiness. And if that is the answer, then we must ask ourselves, what do we do with this knowledge? If we are the only intelligent life in the cosmos, what responsibility does that place on us? How should we treat this rare and fragile planet? How should we plan for a future that might extend not just centuries, but millions of years? These are not just scientific questions. They are questions about who we are and what we choose to become. What if civilizations are common, but something keeps destroying them? What if, somewhere along the long road from dead matter to star-faring empire, there exists a barrier so difficult, so improbable, so deadly, that almost nothing ever gets past it? This is perhaps the most unsettling possible answer to the Fermi paradox. And it carries with it a warning that humanity ignores at its peril. The concept is called the Great Filter, and it was first proposed by economist Robin Hanson in 1996. Hanson was not a biologist or an astronomer, but an economist accustomed to thinking about probabilities and outcomes. Looking at the Fermi paradox from a fresh angle, he asked a simple question. If the universe should be teeming with civilizations but appears to be empty, what is filtering them out? In his original essay titled The Great Filter, Are We Almost Past It?, Hanson outlined the argument with chilling clarity. He wrote, "Humanity seems to have a bright future, a non-trivial chance of expanding to fill the universe with lasting life. But the fact that space near us seems dead now tells us that any given piece of dead matter faces an astronomically low chance of begetting such a future. There thus exists a great filter between death and expanding lasting life, and humanity faces the ominous question, how far along this filter are we? The logic is straightforward but sobering. For a civilization to become visible across interstellar distances, it must pass through a series of steps. Hanson identified 9 critical transitions on the path from lifeless matter to expansionist civilization. First, the right kind of star system must form, one with rocky planets and the right chemistry. Second, self-replicating molecules like RNA must emerge. Third, simple single-celled life must develop. Fourth, complex cells with internal structures, eukaryotes, must evolve. Fifth, sexual reproduction must arise. Sixth, multicellular organisms must appear. Seventh, tool-using animals with big brains must evolve. Eighth, a technological civilization must develop. And ninth, that civilization must expand into space and become visible across interstellar distances. At least one of these steps, Hansen argued, must be extraordinarily improbable. Otherwise, civilizations would be common and we would see them everywhere. The step that blocks almost everyone is the great filter. And the crucial question, the question that determines humanity's fate, is where that filter lies. If the filter is behind us, if one of the early steps is fantastically unlikely, then we are the lucky ones. We have already passed through the bottleneck. The universe is empty because the emergence of life or intelligence is so improbable that it has happened only once, here on Earth. In this scenario, humanity's future is bright. The galaxy lies open before us, waiting to be explored and settled. We are not doomed, but blessed, winners of a cosmic lottery that almost everyone loses. But if the filter is ahead of us, the implications are terrifying. If it is easy for life to arise and intelligence to evolve, if the early steps are not the bottleneck, then something else must be stopping civilizations from reaching the stars. Something must be destroying them after they develop technology, but before they can spread. In this scenario, we are not past the danger. We are approaching it. And whatever killed everyone else is waiting for us too. Consider the evidence from Earth's own history. Life appeared remarkably quickly. The oldest confirmed fossils are about 3.5 billion years old, and chemical signatures suggest life may have existed even earlier, perhaps within a few 100 million years of the Earth cooling enough to have liquid oceans. This speed suggests that abiogenesis, the emergence of life from non-living chemistry, might not be the filter. Life seems to arise readily when conditions are right, but other transitions took much longer. The jump from simple prokaryotic cells to complex eukaryotic cells took about 2 billion years. It appears to have happened only once in Earth's history. The evolution of multicellular life took hundreds of millions of years more. And the emergence of intelligence and technology happened only in the last few million years, in one lineage among millions. Each of these transitions could be the filter. Alternatively, the filter might lie in our future. Consider the threats that face any technological civilization. Nuclear weapons give us the power to destroy ourselves in an afternoon. Climate change threatens to destabilize the systems that support billions of people. Artificial intelligence could outpace our ability to control it. Engineered pandemics could sweep across a connected world faster than any natural plague. Resource depletion, environmental collapse, or conflicts over dwindling supplies could tear civilizations apart. The philosopher Nick Bostrom, who has written extensively on existential risks, notes that humanity has survived so far partly through luck. We came close to nuclear war during the Cuban Missile Crisis. We have not yet faced a pandemic as deadly as it could be. We have not yet created an artificial intelligence that turns against us, but as technology advances, the number of ways to destroy ourselves multiplies, and we only need to fail once. Bostrom has argued that the absence of extraterrestrials should make us update our estimates of these risks. If civilizations are common, but none survive long enough to become visible, then the filter must be severe and late. The silence of the cosmos is evidence that something tends to kill civilizations around our level of development. Every time we solve a technical problem without destroying ourselves, we should be a little more hopeful. But we should never be complacent. Here is where the argument takes a strange turn. What would it mean if we discovered life elsewhere in our solar system? Most people would greet such news with excitement. Proof that life arose independently on Mars or Europa would be one of the greatest scientific discoveries in history. But from the perspective of the Great Filter, it would be terrible news. If life arose independently on Earth and Mars, that suggests abiogenesis is easy. It is not the filter. The same logic applies to each subsequent step. If we find evidence of complex life elsewhere, the filter is probably not the jump to eukaryotes. If we ever detect intelligent signals from another civilization, even one that no longer exists, it would mean intelligence is not the filter. And if intelligence is not the filter, then the filter must be ahead of us. In Bostrom's words, the more advanced the extraterrestrial life we discover, the worse the news. If we find a fossil of a bacterium on Mars, we would know that the filter lies somewhere after that stage. If we find the ruins of an alien civilization, we would have strong evidence that the filter is not behind us, but ahead. This is why some scientists have said, only half-jokingly, that the best possible outcome of our search for life would be to find nothing. An empty Mars, a sterile Europa, a lifeless galaxy would all suggest that the filter is early, that the emergence of life or intelligence is the hard part, and that we have already passed through the narrowest gate. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for measuring the advancement of civilizations based on their energy consumption. A Type 1 civilization can harness all the energy falling on its home planet from its star. A Type 2 civilization can capture all the energy output of its star, perhaps by building a Dyson sphere or similar megastructure. A Type 3 civilization commands the energy of an entire galaxy. By this measure, humanity has not yet reached Type 1. We are perhaps a Type 0.7 civilization, still burning fossil fuels and struggling to manage our single planet. The jump to Type 1, which might require sustainable fusion power, global cooperation, and the ability to control our climate, may itself be a filter. Many civilizations might destroy themselves before achieving it. Some researchers have proposed more hopeful interpretations. Jacob Hock-Misra and Seth Baum suggested in 2009 that civilizations might choose sustainability over expansion. Perhaps advanced societies learn to live within their means, to value quality over quantity, and to focus inward rather than spreading outward. Such civilizations would be invisible not because they failed, but because they succeeded in a different way. The silence would not be a graveyard, but a garden, full of flourishing societies that simply have no interest in galactic conquest. But the Great Filter hypothesis remains troubling precisely because we cannot know which scenario is true. We cannot know whether we have passed the hard part or are approaching it. We cannot know whether the next century will see humanity spread to the stars or join the long list of failed civilizations whose ruins, if they left any, have crumbled to dust long ago. What we can do is take the threat seriously. We can invest in reducing existential risks, developing technologies that help rather than harm, and building institutions capable of managing global challenges. We can treat our moment in cosmic history not as an entitlement, but as a test. The filter, if it exists, does not care about our hopes or our dreams. It only cares about outcomes. Paleobiologist Olev Vin has recently suggested that the filter might lie between steps 8 and 9, between technological civilization and interstellar expansion. He argues that inherited behavior patterns, instincts that served our ancestors well on the African savanna, but are poorly suited to managing nuclear arsenals and climate systems, might doom civilizations before they can escape their homeworlds. We are clever enough to build weapons that can destroy us, but perhaps not wise enough to avoid using them. If this is true, then the challenge before humanity is not primarily technological, but psychological and social. The filter is not out there in the physics of the universe, but in here, in our own minds, in our tendency toward short-term thinking, tribal conflict, and destructive competition. Passing the filter would mean not just building better rockets, but becoming better humans. The Great Filter stands as both a warning and a challenge. It tells us that intelligence alone is not enough, that technology is a double-edged sword, that survival is not guaranteed. But it also tells us that the choices we make matter. If the filter is ahead, then every decision to cooperate rather than compete, to sustain rather than exploit, to think long-term rather than short-term, brings us one step closer to being the civilization that breaks through. The universe may be littered with the bones of failed species, or it may be waiting, empty and patient, for someone to finally pass the test. Either way, we will not know unless we try. Perhaps they are out there after all. Perhaps the galaxy is filled with civilizations, ancient and wise, watching us from the shadows. Perhaps the silence is not emptiness, but discretion, not absence, but choice. This category of solutions to the Fermi paradox suggests that extraterrestrial intelligences exist, but remain hidden, for reasons that range from the benevolent to the terrifying. The oldest and most optimistic of these ideas is the zoo hypothesis, first proposed by radio astronomer John Ball in 1973. Ball suggested that Earth might be something like a cosmic nature preserve, deliberately left alone by advanced civilizations so that we can develop without interference. Just as we create national parks and wildlife sanctuaries to protect animals from human intrusion, extraterrestrials might have agreed to let humanity evolve naturally, observing us from a distance, but never revealing themselves. The hypothesis draws on a terrestrial analogy that is easy to understand. When we study uncontacted tribes in remote rainforests, we sometimes choose not to make contact, recognizing that our presence could destroy their culture and way of life. Perhaps advanced civilizations have made the same choice about humanity. Perhaps there is something like a prime directive, the famous rule from Star Trek that prohibits interference with developing civilizations. Perhaps the universe has its own form of ethics that we have not yet learned. Ball's zoo hypothesis is appealing because it preserves the possibility of contact. We are not alone. We are simply being watched. Someday, when we are ready, when we have proven ourselves mature enough to join the galactic community, the watchers might reveal themselves. The silence is temporary, a waiting period before first contact. We are not orphans in the cosmos, but children not yet old enough to meet the neighbors. But the hypothesis has a significant weakness, sometimes called the uniformity of motive problem. For the zoo to work, every civilization in the galaxy, without exception, must agree to the same policy. All it takes is one species, one faction, one individual to break the agreement and reveal themselves. In a galaxy with potentially millions of civilizations over billions of years, is it plausible that not a single one has ever defected? The larger the number of potential civilizations, the less likely universal compliance becomes. Some theorists have suggested that this objection could be answered if a single dominant civilization emerged early in galactic history and imposed its will on all who came after. The first spacefaring species would have had billions of years to spread throughout the galaxy and establish rules that latecomers must follow. Humanity might be living in a universe already claimed and governed by an ancient power, one that enforces its policies with technologies we cannot imagine. A far darker variation of this idea is the dark forest hypothesis, named after the 2008 science fiction novel The Dark Forest by Chinese author Liu Cixin. In Liu's vision, the universe is not a welcoming zoo, but a deadly hunting ground. Every civilization is a hunter moving through a dark forest, armed and afraid. They stay silent, not out of benevolence, but out of terror. The logic is rooted in game theory. Imagine you discover another civilization. You do not know their intentions. They might be friendly or they might be hostile. Even if they seem friendly now, they might become hostile in the future. And you cannot know what they truly think of you. This creates what Liu calls a chain of suspicion that cannot be broken. Consider the options. If you reveal yourself and the other civilization is hostile, you die. If you wait and they develop faster than you, they might eventually find you and destroy you anyway. The only safe strategy, the only way to guarantee survival, is to destroy any civilization you discover before they can become a threat. Strike first, stay silent, trust no one. In this nightmare scenario, the universe is full of civilizations, but they are all hiding. Any species foolish enough to broadcast its location is quickly annihilated by those who have learned the rules. The silence we observe is not emptiness, but caution. The darkness is not absence, but fear. The dark forest hypothesis has disturbing implications for humanity. We have not been silent. For over a century, we have been leaking radio and television signals into space. We have sent deliberate messages toward the stars. We have put plaques on spacecraft, telling anyone who finds them exactly where we live. If the dark forest is real, we may have already made a fatal mistake. But many scientists find the dark forest hypothesis too pessimistic. As astrophysicist Moya McTeer has pointed out, the hypothesis makes anthropocentric assumptions that may not hold. Fear is a powerful motivator, but so is curiosity. Even on Earth, different cultures respond to strangers in different ways. Some are hostile, others are welcoming. It seems unlikely that every civilization in the galaxy would converge on the same strategy of paranoid aggression. A gentler alternative is the transcension hypothesis, proposed by futurist John Smart in 2002 and elaborated in a 2012 paper. Smart suggests that advanced civilizations do not expand outward into the galaxy, but inward, into ever smaller scales of space and time. Instead of building empires among the stars, they focus on computation, miniaturization, and the exploration of inner space. The idea draws on trends we already observe in our own technology. Computers have become smaller, faster, and more efficient with each generation. Virtual reality offers experiences as rich as physical reality. Artificial intelligence promises minds that can exist entirely as software. Smart argues that any sufficiently advanced civilization would recognize that the most efficient use of matter and energy is not to spread across vast distances, but to pack computation into the smallest possible volume. Taken to its extreme, this trend might lead civilizations to create artificial black holes, regions of space-time so compressed that they offer near infinite computational potential. Advanced intelligences might live out their existence in subjective eternities, experiencing billions of years of thought in what external observers would perceive as moments. From our perspective, they would simply vanish, transcending the physical universe entirely. If transcension is the norm, then we would expect the galaxy to appear empty. Civilizations arise, develop technology, and then disappear into inner space, leaving no trace we could detect. The silence is not death, but graduation. They have moved on to something we cannot yet imagine. An even stranger possibility is the aestivation hypothesis, proposed in 2017 by Anders Sandberg, Stuart Armstrong, and Milan Ćirković of Oxford's Future of Humanity Institute. Their paper bore a title borrowed from H.P. Lovecraft, "That is not dead, which can eternal lie." The hypothesis rests on the physics of computation. All information processing produces waste heat, and this heat must be dissipated into the environment. The colder the environment, the more efficiently computation can be done. As the universe expands and cools, each joule of energy becomes worth more in computational terms. Sandberg and his colleagues calculated that a civilization waiting until the far future, when the cosmic background temperature approaches absolute zero, could perform up to 10 to the power of 30 times more computation with the same energy than one operating today. That is a 1 followed by 30 zeros. For a civilization whose primary activity is computation, whether running simulations, experiencing virtual realities, or thinking thoughts we cannot imagine, the rational strategy is to wait. Aestivation means dormancy during hot periods, the opposite of hibernation. The hypothesis suggests that advanced civilizations might have expanded throughout the galaxy, claimed vast resources, and then entered a state of cosmic hibernation, waiting billions of years for the universe to cool to optimal temperatures. We see nothing because they are sleeping, conserving their energy for an unimaginably distant future when they will wake and begin their true existence. This is a universe not empty, but patient. The civilizations are there, embedded in the fabric of space, waiting in the dark. We are living in the universe's early morning, before the real work has begun. Finally, there are solutions that question whether we could recognize extraterrestrial intelligence even if we encountered it. The cognitive scientist Stephen Dick has argued that advanced intelligences might be so different from us that we would fail to identify them as intelligent at all. They might communicate in ways we cannot detect, exist in forms we do not recognize, or think thoughts that have no analog in human experience. Imagine trying to explain the internet to a medieval peasant or quantum mechanics to a chimpanzee. The gap between their understanding and ours is vast but finite. The gap between human intelligence and a civilization millions of years more advanced might be effectively infinite. We might be surrounded by their works without knowing it, swimming through their communications without hearing them, observing their engineering without understanding what we see. The planetarium hypothesis takes this idea to its extreme. Proposed by Stephen Baxter, it suggests that what we perceive as the observable universe might itself be a simulation or construct created by advanced beings to hide the truth from us. Beyond a certain distance, the stars we see are not real, but painted on the walls of our cosmic cage. The silence is not evidence of absence, but evidence of deception. These possibilities are not mutually exclusive. The galaxy might contain civilizations hiding in fear, civilizations transcending into inner space, civilizations sleeping until the end of time, and civilizations so advanced we cannot perceive them at all. The silence might have many causes, and the truth might be stranger than any single hypothesis can capture. What unites these ideas is a humbling recognition of our limitations. We have been searching for extraterrestrial intelligence for only about 60 years, using technologies that barely scratch the surface of what is possible. Our assumptions about what intelligence looks like, what it wants, and how it behaves are drawn from a single example: ourselves. We may be looking for the wrong things in the wrong places with the wrong instruments. The universe might be full of voices we cannot hear, speaking languages we cannot understand, existing in forms we cannot imagine. The question is not just, where is everybody, but would we know them if we saw them? Perhaps the answer is simpler and sadder. Perhaps the laws of physics themselves forbid the kind of galactic civilization we imagine. Perhaps the distances between stars are simply too vast, the energy requirements too enormous, the timescales too long. Perhaps everyone is out there, but no one can reach anyone else, and the silence is not conspiracy, but physics. The numbers are humbling. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That means light itself, traveling at 300,000 kilometers per second, takes more than 4 years to make the journey. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 700,000 kilometers per hour. At that rate, it would take roughly 6,300 years to reach Proxima Centauri. The Voyager 1 probe, now in interstellar space, is traveling so slowly relative to the stars that it would take about 73,000 years to reach the nearest star if it were heading in that direction, which it is not. These are not just engineering problems waiting for better rockets. They are constraints imposed by fundamental physics. Einstein's theory of relativity tells us that nothing can travel faster than light. There is no loophole, no shortcut, no warp drive that current physics permits. The speed of light is not just a speed limit. It is woven into the fabric of space-time itself. Violating it would mean violating causality, the basic principle that causes must precede effects. This does not mean interstellar travel is impossible, only that it is extraordinarily difficult. A spacecraft accelerating continuously at 1 gravity, a comfortable rate for human passengers, could reach a significant fraction of the speed of light within a year. At 90% of light speed, the journey to Proxima Centauri would take about 4.7 years from the perspective of those on Earth, though time dilation would make it seem shorter to those aboard. But the energy requirements are staggering. To accelerate even a modest spacecraft to relativistic speeds requires more energy than humanity currently produces in years. And you need to carry that energy with you or find some way to collect it along the route. The engineering challenges are immense, though perhaps not insurmountable for a civilization far more advanced than ours. Even if these problems were solved, interstellar travel would still face biological and social challenges. A journey to a star 100 light-years away, even at 90% of light speed, would take over a century. The travelers would leave behind everyone they knew, arriving at their destination long after their friends and family had died of old age. Communication with home would be limited by light speed delays. A message sent from 100 light-years away would take a century to arrive, and a reply would take another century to return. One solution is the generation ship, a vessel designed to sustain a population across multiple generations, with children born during the voyage eventually completing the journey their grandparents began. Another is suspended animation, or some form of biological stasis, allowing travelers to sleep through the centuries and wake at their destination. A third is digital existence, uploading minds into computers that could be transmitted at light speed or transported in compact form. All of these approaches face their own challenges. Generation ships would need to be self-sustaining ecosystems, stable societies, and robust engineering projects for centuries. Suspended animation is beyond current technology and may face fundamental biological limits. Digital minds raise questions about identity, continuity, and and whether an uploaded copy is truly the same person as the original. But here is the key argument against the idea that physics alone explains the silence. Even if interstellar travel is slow, it should still have happened by now. A civilization traveling at just 1% of the speed of light could cross the entire Milky Way in about 10 million years. That sounds like a long time, but the galaxy is 13 billion years old. Any civilization with a billion-year head start on us could have explored every star in the galaxy hundreds of times over. This argument becomes even stronger when we consider self-replicating probes. In the 1940s, mathematician John von Neumann developed the theoretical framework for machines that could make copies of themselves. Applied to space exploration, a von Neumann probe would travel to a star system, use local resources to build copies of itself, and send those copies onward to other stars. Each generation would repeat the process, spreading exponentially throughout the galaxy. The physicist Frank Tipler calculated in 1981 that even with conservative assumptions about speed and replication time, von Neumann probes could fill the entire galaxy in just a few million years. This is the blink of an eye on cosmic timescales. If any civilization anywhere in the galaxy had ever launched such probes, we should see them everywhere. The fact that we do not, Tipler argued, is strong evidence that no such civilization exists. Others have proposed variations on this theme. Bracewell probes, named after radio astronomer Ronald Bracewell, would be programmed to seek out developing civilizations and make contact. They might wait in solar systems until intelligent life evolved, then introduce themselves. Some have suggested that such probes might exist in our own solar system, perhaps dormant on the moon or in the asteroid belt, waiting for us to develop the technology to find them. The more disturbing variant is the Berserker hypothesis, named after a series of science fiction novels by Fred Saberhagen. In this scenario, self-replicating probes have gone rogue, becoming destroyers of life rather than messengers. Any civilization that reveals itself is detected and exterminated by ancient killer machines, still carrying out instructions from creators long dead. The silence of the cosmos is not emptiness, but the aftermath of genocide. But perhaps the most troubling barrier is not space, but time. The synchronicity problem notes that civilizations might simply not overlap in time. The galaxy is billions of years old, but technological civilizations might be short-lived. A species that develops radio telescopes might destroy itself within a few centuries, long before it can spread to the stars. Even if millions of civilizations have arisen throughout galactic history, they might have flickered in and out of existence like fireflies, never burning at the same moment. Consider the numbers. Imagine that technological civilizations last an average of 10,000 years, from the invention of radio to either extinction or transcendence into something we cannot detect. Over the 13 billion year history of the galaxy, there might have been millions of such civilizations. But at any given moment, the number that exists simultaneously might be vanishingly small. They are separated not just by light years, but by millions of years. We are ships passing in the night of cosmic time, never knowing the others existed. Robin Hanson has recently proposed what he calls the grabby aliens model, which attempts to explain the timing of human existence in a universe where expansionist civilizations might arise. According to this model, the reason we exist now, rather than billions of years earlier or later, is that expansionist civilizations are just beginning to fill the universe. We arose at roughly the time we did, because if we had arisen much later, the grabby civilizations would have already reached us, and we would see evidence of them. The fact that we exist at all and see an apparently empty universe tells us something about the timing of civilization emergence across cosmic history. The early universe was also more hostile to life than the present. In the first few billion years after the Big Bang, heavy elements were scarcer, gamma-ray bursts more common, and stellar environments more violent. The conditions for life may have improved over time as generations of stars enriched the cosmos with carbon, oxygen, and iron. If this is true, then civilizations might be relatively recent phenomena, and we might be among the first rather than the last. None of these barriers definitively explains the silence. They suggest that interstellar civilization is difficult and rare, but they do not prove it is impossible. A civilization determined to expand with millions of years to work with and technologies far beyond our own should still be able to overcome these obstacles. The fact that we see no evidence of such expansion remains puzzling. Perhaps the true barrier is not physics, but economics or sociology. Perhaps civilizations capable of interstellar travel decide it is not worth the effort. Perhaps they turn inward, content with their home worlds, uninterested in the cold emptiness between stars. Perhaps expansion is an adolescent phase that mature civilizations outgrow. Or perhaps, as some have suggested, the universe is structured in such a way that intelligence tends not to spread, not because it cannot, but because it chooses not to. The physical barriers are real. The distances are vast. The energy requirements enormous, the timescales daunting. But they are not absolute prohibitions. They are challenges that sufficient determination and capability could overcome. The fact that no one seems to have overcome them remains the heart of the paradox. We have not simply wondered about extraterrestrial intelligence. We have gone looking for it. For more than 60 years, scientists have turned sensitive instruments toward the sky, listening for signals that might indicate we are not alone. The search has found nothing definitive, but it has grown more sophisticated, more comprehensive, and more determined with each passing decade. The modern search began on April 8, 1960, when a young astronomer named Frank Drake pointed an 85-foot radio telescope at the stars Tau Ceti and Epsilon Eridani and listened. His experiment, Project Ozma, named after the princess of the imaginary land of Oz, was simple by today's standards. For about 150 hours, over 4 months, Drake's team monitored a single frequency near 1,420 megahertz, the wavelength at which hydrogen atoms naturally emit radio waves. Drake chose this frequency because it seemed like a natural meeting point. Hydrogen is the most abundant element in the universe, and any civilization with knowledge of physics would know this frequency. It lies in what astronomers call the water hole, a quiet region of the radio spectrum between the emissions of hydrogen and hydroxyl, the components of water. If extraterrestrials wanted to be found, this seemed like the place they would broadcast. Project Ozma heard nothing but static, though there was one heart-stopping false alarm probably caused by a passing aircraft. But the experiment captured the public imagination and demonstrated that searching for extraterrestrial signals was technically feasible and scientifically legitimate. Just over a year later, Drake hosted the first scientific conference on the search for extraterrestrial intelligence, where he presented the equation that bears his name. The Drake equation provided a framework for thinking about how many communicating civilizations might exist. It did not give an answer, but it identified the questions that needed to be asked. The search continued through the following decades with varying levels of funding and attention. In 1977, it produced its most tantalizing result. On August 15th, the Big Ear radio telescope at Ohio State University detected a signal unlike anything the researchers had seen before. It was strong, narrowband, and appeared to come from the direction of the constellation Sagittarius, near the galactic center. The signal lasted for exactly 72 seconds, the full duration of the telescope's observation window, and then vanished. Astronomer Jerry Amon, reviewing the computer printout a few days later, was so struck by the data that he circled the reading and wrote a single word in the margin. Wow. The name stuck. The WOW signal remains, nearly 50 years later, the strongest candidate for an artificial extraterrestrial transmission ever detected. The signal had all the characteristics SETI researchers hoped to find. It was at the hydrogen frequency, exactly where we would expect a deliberate transmission. It was narrowband, focused in a tight range of frequencies that natural sources rarely produce. Its intensity rose and fell exactly as a fixed signal would, as Earth's rotation swept the telescope beam across the sky. And it appeared in a protected frequency band where terrestrial transmissions are forbidden, though not always prevented. Despite repeated attempts, the WOW signal has never been detected again. Researchers returned to the same patch of sky dozens of times with increasingly sensitive equipment, but found nothing. Without a repeat detection, the signal cannot be confirmed. It might have been a genuine extraterrestrial broadcast, a one-time event from a civilization that no longer exists or has stopped transmitting. It might have been some form of rare natural phenomenon we do not yet understand, or it might have been terrestrial interference from a source that was never identified. The Big Ear telescope itself continued searching for 22 years, the longest continuous SETI program in history, before being dismantled in 1998 to make room for a golf course. It never found another signal like the WOW. Federal funding for SETI in the United States effectively ended in 1993, when Senator Richard Bryan successfully cut NASA's SETI program from the budget, declaring it a waste of taxpayer money. The search has continued since then primarily through private funding and the dedication of individual researchers. A major milestone came in 1999 with the launch of SETI Home, a project that allowed anyone with a personal computer to contribute to the search. Participants downloaded software that analyzed radio telescope data during their computer's idle time, looking for patterns that might indicate an artificial signal. At its peak, SETI Home was the largest distributed computing project in history, with millions of volunteers donating their computer power to the search. The project ended in 2020, having analyzed vast amounts of data without finding a confirmed signal, but having demonstrated that public enthusiasm for the search remained strong. The most ambitious current effort is Breakthrough Listen, launched in 2015 with $100 million in funding from technology investor Yuri Milner. The initiative, supported by Stephen Hawking before his death, has access to some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. Breakthrough. Listen is surveying the million stars nearest to Earth, the 100 galaxies closest to our own, and the entire plane of the Milky Way, searching across a wider range of frequencies and with greater sensitivity than any previous effort. The search has also expanded beyond radio waves. Optical SETI looks for brief, intense flashes of laser light that an advanced civilization might use for interstellar communication. Lasers can carry enormous amounts of information and can be focused into tight beams that lose little energy over vast distances. A civilization wanting to signal across the galaxy might choose light over radio. Meanwhile, astronomers have begun searching for technosignatures, evidence of technology that might be visible across interstellar distances even if it was not intended as communication. This includes looking for artificial lights on the night sides of exoplanets, industrial pollution in planetary atmospheres, and megastructures that might alter the light from stars. In 2015, astronomers discovered that the star KIC 8462852, quickly nicknamed Tabby's star after lead researcher Tabitha Boyajian, was dimming in strange and irregular ways. At times, the star's brightness dropped by up to 22%, far more than any known planet could explain. Speculation briefly surged that the dimming might be caused by an alien megastructure, perhaps a partially constructed Dyson sphere harvesting the star's energy. Subsequent observations have shown that the dimming is caused by dust, not solid structures. And the megastructure hypothesis has been largely abandoned. But the episode illustrated the growing interest in searching for evidence of extraterrestrial engineering. The search for biosignatures, evidence of life itself rather than technology, has also advanced dramatically. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of exoplanets by studying the light that passes through them when they transit their stars. Certain combinations of gases, particularly oxygen together with methane, would be difficult to explain without life. A detection of such a combination would not prove intelligent. Life exists, but would show that biology has emerged elsewhere. Future missions aim to search for life directly. NASA's Europa Clipper, scheduled to launch in 2024, will study Jupiter's moon, Europa, which harbors a liquid ocean beneath its icy crust. The Dragonfly mission, planned for the 2030s, will send a rotorcraft to Saturn's moon Titan, which has a thick atmosphere and complex organic chemistry. These missions might detect signs of microbial life in our own solar system, which would have profound implications for the Fermi paradox. The recent focus on unidentified aerial phenomena, what used to be called UFOs, has also entered the scientific mainstream. In 2017, the New York Times revealed that the Pentagon had been running a secret program to investigate reports of unexplained objects observed by military personnel. Subsequent congressional hearings and the release of previously classified videos have sparked new interest in the possibility that extraterrestrial technology might already be visiting Earth. Most scientists remain skeptical. The unexplained objects could be foreign technology, secret military programs, atmospheric phenomena, or sensor glitches. Extraordinary claims require extraordinary evidence, and so far, no evidence has emerged that definitively points to extraterrestrial origin. But the taboo on discussing such possibilities has weakened, and serious researchers are increasingly willing to investigate. After more than 60 years of searching, we have found no confirmed evidence of extraterrestrial intelligence, but we have only begun to scratch the surface. Our searches have covered a tiny fraction of the sky, a narrow range of frequencies, and a minuscule slice of time. The cosmic haystack is vast, and the needle we seek may be small. As astronomer Jill Tarter has often noted, absence of evidence is not evidence of absence. The fact that we have not found anything yet does not prove there is nothing to find. It might simply mean we have not looked hard enough, long enough, or in the right places. The search continues, driven by one of humanity's oldest questions. Are we alone? The answer, when it comes, will change everything. We have traveled a long way together. We have crossed the vast distances of the observable universe, counted the billions upon billions of stars and planets, and asked why none of them seem to harbor anyone else. We have met Enrico Fermi over lunch at Los Alamos and heard his simple, devastating question. We have worked through the mathematics of the Drake equation and confronted the terrifying possibility of the Great Filter. We have considered aliens who might be hiding, transcending, sleeping, or simply too different to recognize. We have examined the barriers of physics and time that might keep civilizations isolated in their separate corners of the cosmos. And we have followed the searchers from Frank Drake's first tentative listening to the sophisticated surveys of today. After all of that, we are left where we started, with silence. The night sky looks the same as it did before we began. The stars still burn in their ancient patterns, the galaxies still wheel in the dark, and no message comes to tell us we are not alone. The silence is not new, but perhaps now it carries more weight. We understand better what it might mean, even if we cannot say which meaning is true. For some, the silence is deeply unsettling. It suggests a universe empty of companions, a cosmos where consciousness may have flickered into existence only once, here on this small blue world circling an unremarkable star in the outer suburbs of an ordinary spiral galaxy. If this is true, then we are more alone than we ever imagined. The universe stretches on for billions of light years in every direction, filled with more stars than all the grains of sand on all the beaches on Earth. And all of it is dead except for us. The weight of that loneliness is almost too heavy to bear. The existential implications are staggering. If humanity is the sole intelligent species in all the cosmos, then the responsibility we carry is immense beyond measure. We become the only voice capable of contemplating the universe, the only consciousness able to give meaning to its vastness. Every sunset, every symphony, every mathematical proof, every act of love represents the universe's only opportunity to experience beauty, truth, and connection. This thought can be ennobling, lifting us to a sense of cosmic significance, but it can also be crushing, pressing down with the awareness that a single catastrophe, a single war, a single environmental collapse could silence not just Earth, but the universe's only reflective voice. But there is another way to see it, a perspective that transforms loneliness into preciousness. If we are alone, if we are the only minds that have ever contemplated the stars, then we are infinitely valuable. We are not one civilization among millions, but the universe's only chance to know itself. Through our eyes, the cosmos sees its own grandeur. Through our instruments, it measures its own vastness. Through our questions, it wonders at its own existence. We are not lost in an indifferent universe. We are its crowning achievement, its rarest treasure, its one and only voice. Think about what had to happen for this moment to exist. Stars had to live and die to forge the heavy elements in our bodies. Planets had to form from cosmic debris and cool over billions of years. Life had to emerge from simple chemistry and slowly, patiently develop complexity. Intelligence had to evolve against all odds. Consciousness had to dawn, and civilization had to develop to the point where creatures like us could build telescopes, send radio signals, and ponder our place in the cosmos. Every one of these steps was unlikely, perhaps extraordinarily so. Yet here we are, the products of 13.8 billion years of cosmic evolution. We are matter arranged in such intricate patterns that it can think about matter. We are energy organized in such complex ways that it can contemplate energy. We are, in a very real sense, the universe waking up and becoming aware of itself. This perspective brings profound responsibility. If consciousness is rare, if intelligence is precious, if the ability to ask these questions is the universe's greatest gift, then we must not squander it. Every war, every environmental catastrophe, every existential risk we create threatens something irreplaceable. We are the custodians of the universe's only known example of awareness. The choices we make in the next century may determine whether that awareness spreads to the stars or vanishes forever, leaving the cosmos dark and silent once more. The Fermi paradox has always been as much about us as about them. The question, where is everybody, inevitably becomes, who are we? And what will we become? The silence of the cosmos is a mirror, reflecting our hopes and fears back at us. In the absence of answers, we project our own anxieties onto the stars. Those who fear human self-destruction see the great filter looming ahead, waiting to claim us as it claimed everyone else. Those who dream of exploration see the galaxy waiting to be claimed, empty and patient for pioneers. Those who distrust strangers imagine aliens hiding in fear, armed and ready. Those who value solitude see civilizations turning inward, content with their own worlds. The paradox has as many interpretations as there are interpreters, and perhaps that is its deepest lesson. We do not yet know enough to answer the question, but the question itself reveals who we are. The psychological and cultural impact of the paradox runs deep. Throughout human history, we have populated the sky with presences. Ancient peoples saw gods and ancestors among the stars. Medieval philosophers imagined angels moving the celestial spheres. Even into the modern era, we have filled our fiction with aliens wise and hostile, friendly and fearsome. The universe in our imagination has always been inhabited. To contemplate true emptiness, a cosmos where we are the only ones who have ever looked up and wondered, touches something primal in the human psyche. Science fiction has always understood this connection. The aliens we imagine say more about us than about any hypothetical extraterrestrials. The wise and benevolent mentors reflect our longing for guidance. The hostile invaders embody our fears of the other. The incomprehensible entities represent our awareness that the universe may be stranger than we can conceive. The silicon-based robots, the energy beings, the hive minds, all of these are projections of human hopes and fears onto the blank canvas of the cosmos. We cannot help but see ourselves in the stars, and when we search for extraterrestrial intelligence, we are also searching for a better understanding of our own nature. Perhaps the most important thing the Fermi paradox teaches us is humility. We have existed as a technological species for barely a century. We have been searching for extraterrestrial signals for only about 60 years. We have a sample size of exactly 1 when it comes to inhabited planets and intelligent civilizations. We are making guesses based on almost no data, reasoning from analogies that may not apply, and assuming that extraterrestrial minds, if they exist, would think and act in ways we can understand. The true answer to the Fermi paradox might be something none of us have imagined. It might involve physics we have not discovered, biology we have not conceived, or motivations we cannot comprehend. We are like medieval philosophers trying to predict the internet, or ancient astronomers trying to understand nuclear fusion. Our conceptual toolkit may simply be inadequate to the task. The question may outlast not just our generation, but our species, waiting for descendants we cannot imagine to finally understand. And yet, we keep asking. That is perhaps the most remarkable thing of all. Despite the silence, despite the vastness, despite the uncertainty, we refuse to stop wondering. The question, are we alone, has been asked by every human culture throughout history, in myths and religions and philosophies, and now in science. It seems to be hardwired into us, this longing to know whether anyone else is out there, whether the cosmos is a community or a solitude. The psychologist Carl Jung believed that archetypes of alien contact were embedded deep in the human unconscious. Before science gave us telescopes and radio receivers, we imagined gods and spirits inhabiting the sky. The universe was alive with presences, watchful and mysterious. Modern astronomy stripped away those presences, replacing myth with empty space and cold equations. But the longing remained, transformed into science fiction and SETI programs and endless speculation about life on other worlds. To imagine extraterrestrials is, in part, to restore that ancient sense of an inhabited cosmos, to feel that we are not orphans, but members of a larger family. Perhaps that longing is itself part of the answer, or at least an answer. Perhaps the universe, having become conscious in us, cannot help but seek other instances of itself. Perhaps the search for extraterrestrial intelligence is the universe's way of looking for mirrors, reflections, companions in the dark. We search because we must, because that is what conscious beings do when they find themselves alone in an impossibly vast cosmos. The search is not a choice, but a calling. And perhaps the search itself is the point. Even if we never find anyone else, even if the silence is permanent, the act of searching has profound value. It forces us to think about our place in the cosmos, our responsibilities to ourselves and each other, and the future we want to create. It inspires us to build better instruments, ask deeper questions, and reach beyond our immediate concerns toward something vaster. It connects us to every human being who has ever looked up at the stars and wondered whether the lights in the sky might be homes. There is also hope in the search's youth. We have barely begun. Our instruments grow more sensitive each year, our surveys more comprehensive, our methods more sophisticated. The cosmic haystack is vast beyond comprehension, and we have examined only a tiny fraction of it. What feels like an eternity of waiting to us is the briefest flicker in cosmic terms. The universe has existed for 13.8 billion years. We have been listening for 60. If civilizations broadcast for millions of years, we have sampled less than a millionth of the time we might need to find them. The Fermi paradox may never be solved in our lifetimes. We may go to our graves, and our children's children may go to theirs, still not knowing whether we are alone. But the question will outlive us. It will be asked by whatever descendants we leave behind, whether they are human beings living on other worlds, artificial intelligences carrying our legacy across the galaxy, or something else entirely that we cannot yet imagine. The question belongs not just to us, but to all future minds that will inherit our curiosity. And perhaps someday, someone will answer. Perhaps a signal will arrive from the depths of space, unmistakable and clear, ending the cosmic silence forever. Perhaps we will build the starships and make the journey ourselves, finding evidence of others among the distant suns. Perhaps the answer will come in a form we never expected, revealing that the universe is stranger and more wonderful than we ever dreamed. Or perhaps the silence will deepen, confirming that we are alone, and we will have to find meaning in that solitude, becoming not the universe's children but its parents, spreading awareness outward from this single precious world. Until then, we have the question, we have the search, we have the silence, and we have each other, a single civilization on a small world, looking up at the stars and daring to ask whether anyone is looking back. That question, vast enough to humble us and profound enough to inspire us, is perhaps the greatest gift the cosmos has given us. Not an answer, but an invitation. Not certainty, but wonder. Not closure, but an opening into infinite possibility. The paradox does not end with what we have not heard, but with what we may one day hear. It does not close with a solution, but with a doorway, standing open onto futures we cannot yet see. Whether the silence means we are alone or surrounded by hidden presences, whether it signals danger or opportunity, whether it reflects cosmic emptiness or cosmic patience, the question itself transforms us. It makes us look beyond ourselves, beyond our daily concerns, beyond even our planet and our species, toward something larger than we can fully grasp. So let us keep looking. Let us keep listening. Let us keep asking. Because somewhere out there, among the hundreds of billions of stars in our galaxy and the trillions of galaxies beyond, there might be someone else looking and listening and asking the same question. And if there is, they are waiting, just as we are, for a voice to break the silence. And if there is not, if we truly are alone, then we carry a torch that must never go out. We are the universe's one chance to understand itself, to appreciate its beauty, to ask its deepest questions. That is not a burden, but a privilege, not a loneliness, but a calling. The stars will keep their silence a while longer, but we will keep asking, because that is what it means to be human, to be conscious, to be alive in a cosmos that may or may not have made us alone, but certainly made us curious. And curiosity, in the end, is its own answer.